All right, today will be lecture 8 and lecture 9. Lecture 9 is going to be after the break. It's going to be a bit confusing for keeping track of the numbers, but we're going to do both of those today. Lecture 8 is initial orbit determination part 2. We're going to burn through the final of the 3 methods of classical orbit determination that are typically taught. And then we'll take a break, and then we'll switch topics, and we'll get on to lecture 9 after our break. So while I'm getting set up, I will take a brave volunteer to answer me some actually pretty simple and straightforward questions about orbit determination. So this is a great way to get some brownie points on some easy questions. Oh, is nobody feeling brave today?
Sure.
We got someone? All right, appreciate your bravery. Okay, so last time we had talked about 2 methods of orbit determination. Do you remember either of their names?
Uh, Gibbs and Lambert.
Very good. I'm impressed. Good, good. And now, do you remember, just kind of raising the temperature on this a little bit, one of them was if you know 3 position vectors, and the other one was if you know 2 position vectors and the time of flight between them. Do you remember which is which?
Uh, Gibbs is the 3 positions, and then Lambert is the 2 positions and time of flight.
Very good, very good. Now, there's a third one that we're going to discuss today, which is called Gauss's method. So we're going to start writing that down in a moment. And Gauss's method doesn't use positions at all. It uses line of sight measurements. And so here's my final question for you. And this is not a memory question. This is an imagination question. Why is it so cool that we can do orbit determination with line of sight measurements?
Line of sight's like angles sort of relative to the ground, right?
Yep, yep. So what you would measure with a telescope, basically. So
Yeah.
let me draw you a picture real quick, right? That's the Earth. I'm going to draw a better one in a second, but let's say that you're here on the Earth, not to scale, and there's a spacecraft out here, right? And okay, what is the position of that spacecraft? I know I asked this question before. It's like, it's here, right? You've got your reference frame, and we can draw a vector here, and we'll call that vector R. But I'm saying, like, how would you, like you specifically, measure the position of a spacecraft?
I definitely think this is where you're headed with the telescope measurement, but
Aha, but telescopes don't
find it
give
in
you
the
position.
telescope,
Yep,
watch it for
yep,
a
you
little
got it.
while.
You picked up on it. So telescopes will give you a direction, which I'm going to call E hat, but they don't give you a position. The big thing is they don't tell you distance, right? Because direction is 2 components of distance, but you don't have your, or sorry, direction is 2 components of position. It does not give you your range or your distance. So what I'm saying is, if we go back to our initial diagram at the start of lecture 7, this stargazing with the spacecraft streaking by overhead, if you just looked at it and got the azimuth and elevation angles for the first position, and then the second position, and then the third position, and you do need to know the times, time matters, that's enough information. So as drawn, this is actually the setup for Gauss's method. And it turns out that actually finding the position of something in space is quite a bit harder than you'd think. And we're going to spend most of the rest of the class talking about how you do that. Finding the position is no easy task. But taking a line of sight measurement is much, much simpler. And so that's what we're going to be discussing today. Okay, good job. You've earned some brownie points. I appreciate you having a discussion with me about orbit determination. All right, here comes the lecture proper. We're going to start by talking about Gauss's method. Gauss's method. All right. So there once was a fella named Carl. That's an I. Carl Friedrich Gauss, who lived from 1777 to 1855. And he used this method of orbit determination to find the orbit of the first asteroid that humans ever discovered. So anybody who knows that off the top of their head, what's the name of the first asteroid that humans have ever discovered? It's also the biggest asteroid. Any takers? Don't know this one? It's bigger than Pluto, which is why some people are like, that's one more reason why Pluto shouldn't be a planet, because we found asteroids bigger than Pluto. Going once, going twice? No, it's called Ceres. That's Ceres. So Ceres was discovered. It was known about, but Carl Friedrich Gauss used his method to find the orbit of Ceres, or in parentheses, or the first asteroid. Of course, it's not actually the oldest, but it's the oldest within human awareness. In 1801, astronomers found this asteroid. It's so large that it's roughly spherical under its own gravity, as opposed to like other asteroids. So it is planet-like. Um, so the most readily available measurements of planets, spacecraft, and astronomical bodies in general are line of sight measurements. Line of sight measurements. So this is, for example, with a telescope or a camera. So this is just putting out onto paper what we had said before, right? So initial orbit determination using only line of sight measurements. Clean that up for a second. Is called angles only IOD, or sometimes you'll hear this referred to as bearing only IOD. Right? Whenever somebody's lost, they say they need to get their bearings. That's a navigation term, right? Bearing means direction. Angles in this case means like, the angle from the your azimuth and your elevation angles, right? So line of sight is really two angles. So you're using only angles, using only bearings, meaning there's no distances involved. There's no positions involved. So it can't be Gauss's method, or sorry, it can't be Gooding. Ooh, I tripped on my words twice. It can't be Gibbs' method, and it's not Lambert's problem. It's Gauss's method. And then there's other ways of solving this, but Gauss's method was one of the first ones that was kind of come up with. So let's do a little diagram here. Let's get the Earth going. Try a little bit harder to make this a circle. And still not so good. Okay. And so this is going to look like a similar diagram because we've seen this before. You've got the Earth and you've got some unknown orbit tracking around the Earth. And you've got some ground station and you've got some position here. And then this is where it's key because the thing that's doing the orbiting is moving. But remember, so is the ground station. So it's a complicated math problem. And so we're going to call this direction here. Am I going to use the letter? I'm going to use the letter U today. All right, we're going to call this U1. And we're going to call this direction U2. And we're going to call this direction U3 with a little hat on it. There's also some unknown range, rho 1, rho 2, and rho 3. And it's absolutely crucial to remember that the ground station moves too. So our two stargazers, and we're going to go back in a second, our two stargazers from the diagram at the start of lecture 7 are themselves moving, and you absolutely have to take that into account. That's the quickest way to get something wrong when you're doing Gauss's method. And so let's kind of zoom in on this a little bit here. I'm going to do the same diagram, but just looking at one of them, right? Go, it's slightly better. Hmm. 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 So let's just look at this. Here's our ground station. Here's something out in space. I'm going to say that the vector from the center of the Earth to the ground station is Ri. I'm going to say that the distance from the ground station to the observed body, which we have no idea what this is rho I. I'm going to say that the direction is Ui. And I'm going to say that the true position of the orbiting body, be it a spacecraft, asteroid, whatever, is little ri. So we got to be careful. Little ri is the position of the body. Big ri is the position of the ground station. And so our problem looks like this. Given R1, R2, and R3, and U1 and U2 and U3 and T1 and T2 and T3. So you don't just measure the spacecraft or whatever it is, you're also keeping track of what time it is, and you're also keeping track of where you are as a observer on the Earth. If you keep track of all this information, find R2 and V2. And that is the setup for Gauss's method of orbit determination. That's what we're trying to accomplish. Okay, so questions before we move on? That's our introduction, at least. Otherwise, it is about time to start doing some math. All right, so I'm going to leave this diagram up here for a second, and I'm going to start with this. Each line of sight measurement satisfies this equation. And this may or may not be obvious just from looking at this diagram. Part of the reason that I went to lengths to draw this diagram specifically is I want this to be clear, right? The position of the ground station plus the vector from the ground station to the observed body is the position of the observed body. That must be very clear, right? So the vector r plus this vector between them is the vector little r. And this vector between them is some direction ui and some distance rho I. So what I'm saying is that the distance rho times the direction u gives us the vector from the ground station to the spacecraft or the asteroid or what have you. So this is our equation, right? You've got ground station, so we're going to call this a station. This is completely unknown, UNK for unknown. This is measured directly, and then this is also unknown. And they're related to one another. As a matter of fact, if you knew rho I, you've got the position, right? So they're kind of unknowns, but they're coupled, they're related unknowns. Okay. So what this tells us then is that each measurement, and let's just think about this in terms of equations, right? You got to remember equations and unknowns. We have to make sure that we have a well-posed problem before we get started, right? We have here three equations because it's a vector, right? A vector of 3 elements, three equations, and how many unknowns? Well, let's count them. Ri is a vector that's completely unknown, so there's three unknowns, and rho I is one unknown, so that's 4. So each equation gives us three equations and 4 unknowns. Or you can think of it this way, right? Each measurement, if we're counting measurements, gives us 2 pieces of information. Because remember that a unit vector has 2 degrees of freedom. You can think of those as azimuth and elevation angles. And the full state, R2 and V2, is 6 degrees of freedom. Therefore, in general, and there are edge cases where this is not true, 3 measurements are needed. Now, let's explore some other relationships between these vectors, right? So we know that this is the case, and this is the case for, R1, R2, and R3. So you could actually have 9 equations and 12 unknowns, right? Now, there's also, if you might remember from Gibbs' method, what we call the coplanar constraint. So recall from Gibbs' method, the coplanar constraint. What that is saying is that all of the position vectors along an orbit have to be coplanar, which means that one of them would by necessity be some linear combination of the other 2. So we're going to write it like this. R2 is some coefficient C1 times R1, plus some coefficient C3 times R3, where C1 and C3 are the Gibbs coefficients. So this is a review from last time. We've seen this equation before. And we can also use Lagrange coefficients. This is why I like to go over Gauss's method third, is because it uses equations from both of the other 2. We can also use Lagrange coefficients. So we're going to rework things a little bit. I'm going to say that R1 is some F1 R2 plus G1 V2. So if you have information about R2 and V2, then the Lagrange coefficients F1 and G1 will give you enough information to find R1. And then similarly, R3 is some F3 R2 plus G3 V2. Okay. And now if you're keeping track and following along at home, we now have, and you can pause and count these if you want to be sure, 18 scalar equations and 18 unknowns. Each next constraint that we introduce gives us more equations, and eventually the number of unknowns and the number of equations reach an equilibrium. And now it's a simple 18 equation, 18 unknown solution. No, I'm just kidding. It's actually quite a bit more. We're about to go through 4 pages of math, so buckle up. Here we go. We will begin our solution. We begin our solution by finding the Gibbs coefficients as functions of Lagrange coefficients. Essentially combining these equations here. R2 is some function of R1 and R3, but we also know that R1 is some function of R2 and V2, and R3 is some function of R2 and V2. It's kind of a mess. And I'm going to present without derivation that C1, the first Gibbs coefficient, is G3 over F1 G3 minus F3 G1. And similarly, C3 is negative G1 over that same denominator, F1 G3 minus F3 G1. Okay, and you can convince yourself of this. I'm going to skip it for now. A little bit like last time, we're going to go a little bit faster in the interest of getting through this all in one lecture. We will make an important assumption. This is actually critical. We will now make an important assumption that the time between measurements is small. And what does small mean? Well, whenever an engineer says that a number is small, it usually means they're about to cheat at something. Usually means they're about to use, for example, only the first term of a Taylor series expansion, which is exactly what we're about to do. So we're going to take an equation that is very ugly. We're going to do a Taylor series expansion, and then we're going to keep only the first term, right? So that's where we're going with this. Just like when you say that an angle is small, we're about to use the small angle approximation, which is also keeping only the first term of a Taylor series expansion. We're going to briefly break to define some time intervals. Remember, we assume that we know the time that each measurement was taken. I'm going to say that tau 1 is t1 minus t2, that tau 3 is t3 minus t2. So we're mapping everything back to the middle, time 2, r2, v2, right? And tau is t3 minus t1. We do this because it's going to make the math a little bit friendlier in a moment. And so the Lagrange coefficients are to first order. So this is a first order approximation for each of these. F1 is approximately equal to 1 minus 1/2 mu over R2 cubed, and this is the scalar R2, times tau 1 squared. F3 is 1 minus 1/2 mu over R2 cubed, tau 3 squared. G1 is approximately equal to tau 1 minus 1/6 mu over R2 cubed, tau 1 squared, and G3 is tau 3 minus 1 over 6 mu over R2 cubed, tau 3 squared. So again, if you were to look this up in a textbook and follow through, they actually show every single step of the derivation. I'm kind of just dropping some equations in your lap here. But there are other equations for the Lagrange coefficients. You can go through and take the Taylor series expansion of each of those. We're going to assume that any term in these time steps that is larger than, I guess in this case, it's not exactly first order because you're getting these squared terms, but you get the idea. We're doing a lower order approximation using the Taylor series expansion. And that gives us these, which means, if we zoom out for a minute, because I know it's easy to get lost in the math, that we can plug these in to the equations above for C1 and C3, the Gibbs equations, right? The Gibbs coefficients. And so this allows us to approximate the Gibbs coefficients as functions of time. And that looks like this. C1 is approximately equal to tau 3 over tau, 1 plus 1/6 mu over R2 cubed, tau squared minus tau 3 squared. And C3 is approximately equal to negative tau 1 over tau, 1 minus 1/6 mu over R2 cubed, tau squared minus tau 1 squared. There we go. Let's clean that up a little bit. There we go. Okay, great. So what this means is that in our first equation, all the way up, well, not exactly the first equation, but the coplanar constraint, we can now say, okay, R2 is some function of R1 and R3 where the coefficients are known because we can actually plug in and solve for these. Oh, but wait a minute. We run into a problem, right? The vector R2 is some function of the vector R1 and the vector R3. We don't know the vector R1 and we don't know the vector R3. And C1 and C3 are both functions of time and the scalar R2 cubed. So we're not out of the woods yet. We've still got some work to do, but this is a good step in the right direction. We're going to pivot now to talk about the unknown ranges. We next seek the unknown ranges, row 1, row 2, and row 3. We'd like expressions for those. And so again, without derivation, I'm just going to show this to you here. Row 1 is equal to 1 over d naught negative d11 plus 1 over c1 d21 minus c3 over c1 d31. D will be explained shortly, so just bear with me for now. Row 2 is 1 over d naught negative c1 d12 plus d22 minus c3 d32. And row 3 is 1 over d naught negative c1 over c3 d13 plus 1 over c3 d23 minus d33. Okay, great. What the heck do I mean by that? So d naught is equal to u1 transpose u2 cross u3. Some combination of u1, u2, and u3. D11 is R1 transpose U2 cross U3. D21 is R2, oh, that gets it straight, there we go. Transpose U2 cross U3. D31 is R2 transpose, oh, 3 transpose U2 cross U3. And we're going to make some more room down here. There's more equations coming. D12 is equal to R1 transpose U1 cross U3. D22 is equal to R2 transpose U1 cross U3. D32 R3 transpose U1, that gets a hat, cross U3. You'll never guess what's coming next. It's D13 R1 transpose U1 cross U2. If you're wondering, I'm having just as much fun as you are right now. D23 is R2 transpose U1 cross U2. Finally, D33 is R3 transpose U1 crossed U2. And I am going to rearrange this. I realize that you don't have this capability with your notebook unless you're taking notes digitally. I think this would actually look a little bit prettier if we just move the whole thing. Is that an option? Yeah, we're just going to put this over here. There we go. Looks a little bit better. Maybe not. So this is a lot. But what we're saying here is this, right? If you can compute all of these annoying D terms, which are just some function, if they're all functions of things that we already know, right? U1, U2, U3, R1, R2, R3. We can compute all of these. And what I'm saying then is row 1, row 2, and row 3 are then functions geometrically of things that we know based on, and so you could, kind of follow through the long version of this derivation and convince yourself of this. What this means is if we know C1 and C3, which we do know C1 and C3, they're functions of tau and of R2 cubed. Now we can find row 1, row 2, and row 3. So it's good to zoom out a little bit here, right? We've reached the point where we've set up kind of the dominoes, right? If we can find R2, right, then we can find C1 and C2. Then we can find row 1, row 2, and row 3. And if you know row 1, row 2, and row 3, you know R1, R2, and R3. And if you know that, we can do some other fun stuff with Lagrange coefficients to get R2 and V2, right? So we're setting everything up. The big kind of keystone that needs to fall out, kind of the one block in Jenga that needs to come out before the whole thing can come tumbling down, is R2, the scalar R2, the distance from the center of the Earth to the orbiting body at the second time measurement. So that's what we're after next. It's just good to review that because I realize it's easy to get lost in the derivation here. So the only unknown to find rho I, just going to say rho 1, rho 2, and rho 3, lies inside C1 and C3, and that is R2, which is the norm of the R2 vector, the scalar R2. We're going to introduce one more equation. I know we're getting tired of those. Here's another one. From the problem setup, we can say, hopefully this is clear, not kind of coming out of nowhere. R2 transpose R2 is capital R2 plus rho 2 U2 transpose capital R2 plus rho 2 U2. Okay. All we're saying is R2 transpose R2 is the other side of the equal sign from this equation all the way at the top, right? The position of the orbiting body is the position of the ground statement plus the range times the bearing, right? This hopefully makes intuitive sense. So if we kind of clean this up a little bit, the vector R2 transpose times the vector R2 is just the scalar R2 squared. And if we tidy this up a little bit, this is, well, I guess we could, yeah, we'll skip a step for now. This is the scalar R2 squared, but it's the capital R2, which we assume we know that, plus 2e rho 2 plus rho 2 squared, where e, we're just going to define e really quickly for the sake of making this look a little bit prettier, is R2 transpose U2. So it's a vector dot product. Okay, so what we have here then is an equation for R2, which is a function of something that we know and measure, and then this rho 2, right? And so, but we also know that rho 2 can be computed from 1 over d naught negative c1 d12 plus c d22 minus c3 d32. And we also know that these are functions of these, and these are functions of these, and da, 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 da. So this is where I'm going to say, we're going to skip a step after, excuse me. We're going to give some thanks to Gauss for doing much algebra. We can write a polynomial, an 8th order polynomial, which looks like this. The scalar R2 to the 8th power plus a times the scalar R2 to the 6th power plus b times the scalar R2 to the 3rd power plus c equals 0, where little a is negative capital A squared plus 2a plus R2 squared. Little b is negative 2 mu capital B, and then in parentheses, a plus b. And little c is negative mu squared b squared. But Paul, what is capital A and capital B? Capital A is 1 over d naught negative d12 tau 3 over tau plus d22 plus d32 tau 1 over tau. And capital B is 1 over 6 d naught open parentheses d12 open parentheses tau 3 squared minus tau squared tau 3 over tau plus d32 open parentheses tau squared minus tau 1 squared tau 1 over tau close parentheses. Isn't that fun? So somebody other than us got to do the algebra to prove this to themselves, and we're going to take their word for it. Or if you want to go and convince yourself this is the case, that it's absolutely an exercise left to the reader. But here's my point, right? This looks ugly, but here's my point. we know all the taus, we know all the d's, we can compute those. Okay? That means that we can compute A and we can compute B. That means that we can compute little a and little b and little c. That means that we've arrived at an 8th order polynomial that we can solve for R2. And that means that if we know that, then we can go back and solve for C1 and C3. And if we know those, we can solve for row 1, row 2, and row 3. And if we know those, it feels like some sort of like Rube Goldberg machine, but it all cascades downhill to R2 and V2, right? So what that means is we're done. We're just going to summarize now. If you're interested, I'm going to show you a way to solve this polynomial with an initial guess and iteration. However, a more modern way to do it would be to just use, like, there's a MATLAB command called roots, the roots of a polynomial, that sort of thing. So let me just summarize what I just said out loud. While this is indeed ugly, we can find the polynomial coefficients A, B, and C, right? It's doable. It's painful, but it's doable. Then we can solve for R2. Now, this is where I need another brave volunteer. I recognize that we've been going for a while. Y'all are getting tired. Don't worry, we're almost done. I need a brave volunteer who can answer me a question about polynomials. Or I can.
I'll go.
You got it, Talia? Okay, nice. What's the problem we're about to run into when we try to solve an 8th order polynomial for R2?
Would it have something to do with like the error or something?
Error could be a concern. I'm going to say that we're allowed to use MATLAB in this. And if you didn't have MATLAB, there's, other nonlinear iteration schemes you can use. Let's assume that there's a MATLAB or Python function that if you give it the polynomial, it will just magically give you the answers. And they're right. They're correct, like just magically, right? There's still a problem. Any other thoughts?
The amount of like initial conditions you would need to solve it.
You're getting close. Let me give you another hint. When you have a parabola, right, like at x squared plus something x plus something, like a second order polynomial,
Yeah.
how many solutions does a second order polynomial have?
2.
How many solutions does a third order polynomial have?
3.
How many solutions does an 8th order polynomial have?
8.
8. Now, I can tell you right now, and this is cheating, that not all 8 of them will be positive real solutions. Some of them will be imaginary, some of them will be negative, but you might still run into a situation where you have multiple reasonable looking answers for R2. And that's going to be a big problem, right? And so we're going to discuss that in a second. But thank you, Atalia. I appreciate you having a discussion about polynomials with me. So here are 2 ways you can solve this, right? 2 ways you can kind of cope with that problem. And so I'm going to make a note. There exists, backwards E is math for there exists multiple solutions. So one possibility is start with a reasonable initial guess and iterate. And you will find the solution that is closest to your reasonable initial guess. Another is to just have something like MATLAB pop out all the solutions, and you can kind of judge them based on what you think is the most reasonable. But this is definitely like a weak link in the chain here, for sure. Here's a method of iteration, right? So R2 I plus 1 is equal to R2 I. Oh, you know what? Hang on. Never mind. We're going to do the iteration this way. Apologies if you already wrote it the other way. It's about to get really ugly if we don't. Minus R2I to the 8th plus A R2I to 6 plus b r2I cubed plus c, and then this is all over 8 r2I to the 7th plus 6a r2I to the 5th plus 3b r2I squared. And so it should make sense that the denominator is the derivative of the numerator, right? This is using like a Newton iteration. So you would start and then iterate until you converge. This is one way of doing it, right? Once we have R2, we can find rho I, the unknown ranges, and then the positions Ri. And so there's one final step, rearranging the Lagrange coefficients from the beginning of this derivation we can say that V2 is equal to 1 over F1 G3 minus F3 G1, and then in parentheses, negative F3 R1 plus F1 R3. Now you might just say, Paul, if we have R1, R2, and R3, why don't we just use Gibbs method to solve this, right? Like we just did all this math. We found R1, R2, and R3. Now you're telling us to use Lagrange coefficients, but like, isn't the end of this whole journey just the beginning of the Gibbs method journey? And the answer is absolutely you could do that, but Gauss couldn't. Gauss, 1777 to 1855. Gibbs, 1839 to 1903. Gauss's method is older than Gibbs' method. Oh, wrong one. So that's a very, if anybody was thinking that, kudos to you for being on the right wavelength, but this method is older. And so this is another way of doing it. So let's summarize everything we just learned. To summarize, the procedure looks like this. Number 1, compute tau 1, tau 3, and tau from measurement times. Number 2, compute 10 scalar terms dij from ui and ri. Next, compute a, b, and e, and then the coefficients little a, little b, little c. Next, solve for the scalar R2 using a reasonable initial guess. Next is 5. Find Gibbs coefficients C1 and C3. Number 6 is find the unknown ranges, rho I. Number 7, find orbiting body positions, Ri. Number 8, approximate, because remember, it's a first order approximation or a kind of lower order approximation, the Lagrange coefficients. F1, F3, G1, and G3. Finally, find V2, and optionally your R2 and your V2 can be used to find theta 2, E, A, big omega, I, and little omega. And that's it. That is Gauss's method. And that is a great natural stopping point. However, we're actually less than, well, maybe 5 minutes away from the end of all of our discussion of initial orbit determination. So we're going to keep on chugging, and then we're going to take a break. So I appreciate y'all having some patience with me. We're going to have a very brief discussion of one other method of orbit determination with absolutely no equations. I just want to make sure that you're aware of one other method of orbit determination. And there's several. I mean, this is still, if you look at the papers that I put in the Google Doc, looking at the journal and conference papers for you to review for your term paper or your term project, this orbit determination is absolutely still an area of active research. You'll find papers published in the last 5 years talking about this. So it's definitely still something that people are thinking about. There's always better and better ways of solving this. Any questions about Gauss's method, or are we happy to have this behind us? All right. Otherwise, we're going to discuss something called Gooding's method. So we will briefly discuss a more modern IOD technique developed by R.H. Gooding in 1993. Pretty recent compared to like 1801. This is another approach to angles only IOD. That's an I. Another approach to angles only IOD. So it's solving the exact same problem as Gauss's method, right? But it uses a different technique. And Gooding's method is considered by many to be the gold standard today. Just to be clear, this is the exact same problem setup as Gauss. So the idea is something like this. What if we just guess? We just guess row 1 and we guess row 3. And we know that we're wrong, but we're guessing, right? Let's scroll up for a little bit. Well, that's a lot of math. If you guessed row 1 and you guessed row 3, that would mean that you also have a guess of R1 and you have a guess of R3. And if you know R1 and you know R3 and you have the time between them, aren't we back to Lambert's problem, essentially? So what you could do is you could guess row 1 and row 3. You know that you're wrong. And then you can solve Lambert's problem. And then you could find R2, which is wrong because you knew that you started with just a complete wild guess for row 1 and row 3. And then estimate U2, right? So if you know, like, okay, if I was right about row 1 and row 3, I solve Lambert's problem, I estimate R2, and then I estimate U2, the middle measurement. Wouldn't the middle measurement match what I saw? Right? Because you have 3 measurements. You've only leveraged 2 of them so far. You use the third one to check your answer, essentially. And so the idea is iterate on row 1 and row 3. And you could even use something like gradient descent optimization in this case. Iterate on row 1 and row 3 until U2 predicted matches U2 measured. That's the idea. I want you to be aware of it. I want you to be aware that that's more popular these days than Gauss's method. We're not going to go into any equations. That's good enough. I want you to be aware of it. There's also something that's worth being aware of. It's not even necessarily taking notes on, worth taking notes on, but Gauss's method and Gooding's method both, and actually this is a more general problem. This becomes clear if you actually start working through the equations. It absolutely falls apart in the very rare case that your observer, which is on the Earth, is coplanar with the orbit. So if you're standing on the equator and the spacecraft is perfectly orbiting the equator of the Earth, all of your measurements are going to be in the same plane. Yes, all the positions are going to be in the same plane, but so are all of your measurements. In that case, Gauss's method falls apart. And so does Gooding's method. It's a more general problem. And you wind up having to use some more exotic techniques to work on that, which included among those exotic techniques are some things that I worked on in my dissertation. And so there's not taking all the credit. Myself and some other people developed some coplanar angles only IOD techniques. Thought I'd toot our horns for a second there. But anyway, that is the conclusion of our discussion on initial orbit determination. I think we all deserve a break here. Any questions before I kind of stop on this and we take a 5-minute break?
You scroll back up to like the equation for like V.
Equations like
Yeah, that one. Yeah.
right here.
Yeah.
Yeah.
Thanks.
Absolutely. I'll leave that on the screen for a little bit. Anybody else? Doing good? All right. I'm going to stop the recording and then we will take a brief intermission here. Let's see here. Just let me know when I'm good to stop sharing the screen here, Merritt. And just as a reminder, I'll be posting all these lecture notes as well, of course, like usual. All right, I'm gonna stop here, but I'm gonna leave this up. Just give me 1 second. There, we'll stop the recording, and then when we come back, it will technically be lecture 9, so we'll have an entirely different recording. We'll just split it up. All right, here we go.